Hi, I'm Rainy, and today we are focusing on the critical component of ship steering as covered in our ship structure course DKN 40173, the rudder. The rudder is an essential part of the aft end constructions. The aft end structure is designed to provide a smooth flow of water both into and away from the propeller. The propeller and the rudder are supported at this after end and require specific structural arrangements. Rudder designs are classified primarily by the position of the rudder blade relative to its turning axis. This classification is key to how the rudder operates and the power required to steer it. The goal of different types is to achieve a reduction in torque by bringing the center of lateral pressure closer to the turning axis. The first type is the unbalanced rudder. This is defined as a rudder where all of its area is positioned aft of the turning axis. Next, the semi-balanced rudder. This type has a small part of its area, specifically less than 20%, located forward of the turning axis. This partial forward area begins to help in reducing the torque required to turn the rudder. Finally, the balanced rudder. This is a rudder where more than 25% of the rudder area is positioned forward of the turning axis. This configuration is the most effective of achieving the desired reduction in torque. Crucially, the stern frame is the heavy structure at the ship's extreme end. Its design is influenced by both the stern profile and the rudder type. It is essential for there to be adequate clearance between the propeller and the stern frame to prevent serious vibrations. The stern frame itself might be cast, forged, or fabricated from steel, plate, and sections. The ship rudder is far more than just a blade. It is a precisely engineered component whose classification, unbalanced, semi-balanced, or balanced dictates the necessary steering machinery or the vessel's overall maneuverability. Thank you for watching.
Ever wonder how a 200,000-ton ship actually turns? It's not magic. It's a slab of metal called the rudder hiding at the stern doing all the steering work. Here's the hook. The rudder barely moves a few degrees. That tiny tilt can swing a skyscraper-sized vessel. Quick explain. Water flows past the ship. Angle the rudder and it deflects flow, creating sideways force, lift, like a wing underwater. That sideways force pushes the stern one way, the bow swings the other, boom, the ship turns. Unbalanced rudders hinge at the front and are harder to move. Balanced rudders put area ahead of the hinge so water helps push it. Semi-balanced, same idea. Spade rudders hang free with a strong stock. Skeg-hung rudders add a fin for protection. Flap rudders add a trailing mini-flap for extra bite at low speeds. Flettner rudders, special rotor-assisted types. Steering gear, massive hydraulic rams, or electric hydraulic systems moving a tiller that twists the rudder stock. Bridge orders are in degrees. 10, 20, 30. Hard over is about 35 degrees. Go past that and flow can stall. More angle doesn't mean more turn. Propellers matter. With power ahead, the prop wash slams onto the rudder, super effective even at low speed. Going astern, the wash changes and the rudder loses authority. Single screw ships feel prop walk, a sideways shove. Twin rudders behind twin screws, better control in slow maneuvers. Now visualize. I'm entering a tight harbor at walking speed. I line up early. Rudders love flow. Small helm, a touch of a head thrust, the jet off the prop hits the rudder, swinging the stern like a door. Need a sharper turn? I kick, burst of a head with rudder over, then neutral to coast, repeat until lined up. Emergency? Hard over isn't always the answer. I balance speed. I balance angle. I balance distance. Too much rudder can scrub speed and widen the turn. In a crash stop, engines to full astern while holding the initial rudder can tighten the swing. Timing is everything. So yeah, the rudder, simple shape, giant leverage, the quiet hero behind every smooth